Hi, this is the video for the module number 12. In this video, we're going to continue with a hypothesis test, but now we're going to focus on the population mean. In the previous video from the module number 11, we saw hypothesis test, but for population proportion. In this case, it's going to be for population mean. What is this about? And we are going to see also something different. It's going to be confidence intervals. All right. In this module, we are going to estimate the parameter mu. What is this? Population mean. By using, of course, we are going to use some formulas and other concepts, but essentially, we're going to be estimating the population mean mu by using the sample mean x. So we're going to perform an hypothesis test as we did it for the population proportion. But now the parameter we're going to be estimating is this one. In the previous module, we tried to estimate, or we made the hypothesis for the population proportion that was denoted by P. And beside that, we're going to be using another method, a confidence interval. A confidence interval for mu is an interval that gives you, in general, it gives you an idea about where mu can be. In the corresponding lab for, I think this module has two labs, but in the corresponding, in one of the labs for this module, I went over confidence intervals. Anyway, I'm going to be explaining here how to do them. But essentially, a 1 minus alpha 1% confidence interval for mu is given by this. So even when all the computations are in this video, they're going to be done by using Minitab. This is the formula for the confidence interval. We're going to be using this here. By the way, this notice in this interval, it depends on the sample mean x bar and x bar. And here, all of this is the same number, but here we subtract and here we add. This T alpha over 2 with subscripts, alpha over 2, comma n minus 1, all of this is a number. This is a number from the T distribution. I won't go over so much details about this. Only how to compute that. But essentially, you will have to, it's another distribution very kind of similar to the normal distribution. Fortunately here, everything is going to be given by Minitab. And here we have the same bad with addition. This, all of this is called the margin of error. All right. So again, in this video, we're going to make an hypothesis test for mu, for the population mean, by using the sample mean, and we are going to see also some examples for confidence intervals to estimate the population mean. So let's start with the exercises. All right. Here, example, mice. Scientists often use mice to study human disease and physiology. Parker et al. Studied over 1,000 newborn mice in order to better understand the genetic loci involved in many human diseases. As part of this study, the scientists snipped up to 5 millimeters from the end of each mouse tail for the purpose of DNA collection. The scientists weighed each mouse immediately after snipping its tail. The provided data set lists the weights of the mice after snipping. And then here, when you see this exercise on Achieve, you will have to download the file. Click to download the data in your preferred format. The data are not available. Well, that. Suppose the researchers wish to determine a range of possible values for the weights of newborn mice with recently snipped tails. Use software to construct a 95% t-confidence interval for the mean weight of newborn mice with snipped tails. Give your answer as an interval of the form lower upper rounded to 2 decimal places. All right, how to do this? Well, we have to go to Minitab. Here we are. You have to download the file for this exercise. Then open, worksheet, local file, and there you have mice. And the column with the corresponding weights is this one, the second column. So how do we create here a confidence interval for this? Well, we have to go to Stat, Basic Statistic. You are going to choose one sample T. And then here, choose the column that had the data. In this case, is the column C2. C2, this box perform hypothesis test. We don't need it by now, so you don't have to click that. Then options, confidence level. Notice, Achieve is asking for a 95% t-confidence interval. So here is where you specify the level of confidence. In this case, it's 95, so leave it like that. 95. Alter the hypothesis, leave it like that. We don't need this by now. And then OK, and then OK. And there you have. This is the confidence interval. This is the lower limit and the upper limit. 25.21 and 25.56. So we put 25.21, comma, 25.56. Now, next, complete the sentence to state how the researchers should correctly interpret the t-confidence interval. All right, from when you will have to respond to this, you're going to be able to choose these answers from the answer bank. So how to interpret this? Do we have to choose here? First, the researchers are first this one. 95% confident. That the true population mean weight, this one, of all newborn mice with snip tails. This one. There you have. So now, next example, it is about radioactive cesium 134 and cesium 137. No, cesium, not cesium, right? It's a waste product of nuclear reactors. The study examined the radioactive cesium tissue concentration of a random sample of 15 Pacific bluefin tuna. Funnus orientalis captured off the coast, the coast, of California 4 months after the Fukushima, Japan nuclear reactor meltdown of 2011. The findings in becquerels per kilogram of dry tissue are given in the table. And there you have. Notice here how we have the data. The data, the raw data, It says historically, radioactive cesium tissue concentrations in bluefin tuna have been below 2 BK over per kilogram on average. Do a complete analysis of the data, including a 95% confidence interval. So we have to give this for the mean tissue concentration of radioactive cesium in bluefin tuna of the coast of California 4 months after the 2000 nuclear meltdown. Use your confidence interval to compare these radioactive cesium levels with the historical average. Use the 4 steps process. State what is the mean radioactive cesium concentration in Pacific bluefin tuna 4 months after the nuclear meltdown, and is it higher than historical levels? Plan. We obtain a 95% confidence interval for mu. Solve. Compute the sample mean and standard deviation. All right. First, here in this exercise, you will have to enter the data in Minitab. So I'm going to put it here, for example, in column number 3. You will have to type the data. We have this one, all of this. So it's going to be 4.6, 6.9, 7.9, 8, 9.2, 10.4, 10.6, 11.1, 11.1, 11.3, 12.3, 12.7, 14.2, and 15.6. We're supposed to have 15 values, and yeah, it is the case, right? So first we have to compute here because this a chip is asking for about this, is asking for this. So we need to compute the mean and the standard deviation. How to do that? Go to stat, basic statistics, display descriptive, and use the column C3, this one here. Statistics, the only ones we need by now are the mean and the standard deviation. So okay, and then okay. And there you have 10.26 and 2.891. 10.26 and s, lowercase s, is the standard deviation, 2.89. All right, the degrees of freedom. This df is the degrees of freedom. It's something that we are going to be using to so that we can perform the hypothesis test and to compute the confidence interval. I think in this case is given by is provided by Minitab. Well, we don't have it here. Anyway, no problem. I will explain how to compute this by hand. But first, what is this df? This df means degrees of freedom. Degrees of freedom. And the degrees of freedom always is computed by using n minus 1. In this case, n is equal to 15. You see it? 15. So it's going to be 15 minus 1. That is 14. Now, how to compute the value for the test statistic? By the way, I will explain how to obtain this directly from Minitab, but by now I'm going to do it by hand. This value is x bar minus mu null divided by s divided by square root of n. What is each of these things? X bar is the sample mean. The sample mean is 10.26. This value mu 0 is the hypothetical value according to the problem. So the hypothetical value is where we have it here, 10.26. Wait. No, I'm sorry. I'm doing everything wrong, right? I'm sorry. So this is not what we're looking for. I'm sorry. I got confused. This T with the T from the test statistic for the hypothesis test. I'm sorry. No, we're doing the confidence interval. Yeah, I'm sorry. So to compute this, you will have to use a table. You can use this table. You can look for the values T alpha minus 1, 1 minus alpha, I'm sorry, alpha over 2, comma, n minus 1, is this one here. We're looking for this value, this one. Yeah, I'm sorry, I got confused. We're doing the confidence interval, not the hypothesis test right now. So this is, you have to compute this in this case. How to get the value for alpha? All right, you're going to set 1 minus alpha equal to the confidence interval in this, to the level of confidence. In this case, the level of confidence is what? Is 95%. So 0.95 and solve for alpha. Alpha is going to be 0.05 and then divide alpha by 2. And you're going to get 0.025. And then this one, n minus 1 is 14. So the value we have to look for is t 0.025, comma, 14. With these two values, if you use the table for the table for the table for the t distribution, you will find the value. But we can do it in Minitab. So go to probability distributions, probability density function, or cumulative distribution, the t distribution. Degrees of freedom, 14. The value we weight is store a table of cumulative probabilities. No, I'm sorry, so it should be this one. Stat. Probability distributions, calc. Inverse, single value, with the t distribution, degrees of freedom, 14. And we want 0.025. So with this should work. Then okay. So this is the value 0.025. Oh, this gives you the table, so I'm sorry. Use what you got here. We got this value 2.144, but it's negative, right? Always use this number, but positive. So it's going to be 2.145. There you have. Now, to compute the interval, lower limit and the upper limit, again, you can go to Minitab. Minitab, stat, basic statistic, one sample t. The values now are in C3. Options, confidence level of 95, okay, and okay. And there you have. These are the values we're looking for: 8.66 and 11.86. 8.66 rounded up to 2 digits and 11.86. Eight point six six and 11.86. And then finally, select the best inclusion. We are 95% confident that, what are we talking about here? We're talking about the mean of the mean tissue concentration of radioactive cesium, right? So what you need to identify what the parameter means, right? About the meaning for the parameter in the context of the problem, so that you can state the conclusion. So in this case, it's going to be, we are 95% confident that the mean radioactive cesium concentration in Pacific bluefin tuna for 4 months after the nuclear meltdown is above the historical levels. This one. This part. All right. Let's continue. Other example, margin of error. In this case, remember that I told you before, the margin of error is this part, this one, only this portion in the confidence interval. So I'm going to write it here. Margin of error is only the value t subscript alpha over 2 comma n minus 1 times the standard deviation divided by the square root of n. That is the margin of error. This, by the way, is lowercase s, the standard deviation, right? There you go. So here, essentially, you will have to verify what would happen if we modify the level of confidence and the sample size. It says one method for measuring air pollution is to measure the concentration of nitrogen dioxide, or NO2, in the air. Suppose Nina, an environmental scientist, wishes to estimate the NO2 concentration in Kiev, Ukraine. She randomly selects 40 locations throughout the city. The city measures the NO2 concentration at each location. Based on her 40 samples, she computes the margin of error for a 95% confidence interval for the mean concentration of NO2 in Kiev in milligrams over cubic meters to be 3.17. So she computed this, and she got, with this information, with n equal to 40, with 95% confidence level equal to 0.95, and what else? The standard deviation, we need it. Based on her 40 samples, she computed the margin of error for to be 3.17. It is not provided, right? So she used these two values, and she got margin of error equal to 3.17. So next, what we have to do here, we will have to play a little with the numbers. For example, here it says what would happen to this number if Nina decreases the confidence level to 90%. In this case, what is going to happen? This number is going to decrease. Why? Because the value for t is going to be lower. So in this case, you can verify that if you compute the value for t, multiply this, or only by paying attention to the formula. In this case, it's going to be decreased. What happens if Nina increases the confidence level to 99%? It's going to increase because this number would increase, this t alpha over 2n minus 1. Nina decreases the sample size to 31 locations. Then Nina decreases the sample size to 31 locations. Oh, well, this is from common sense. If we increase the sample size, yeah, then this denominator is going to be greater. If you divide something by a very big number, then eventually that is going to be small. So in this case, if we decrease that, then this number is going to be greater, right? So that means that this is going to increase. And this one, if Nina increases the sample size, this is going to decrease. And there you have. Essentially, here is only what would happen if we play a little with the margin of error and some of the components for that formula. Example, student wildlife. A student in wildlife management studied trout habitat in the upper Shavers Fork watershed in West Virginia. The springtime water pH of 29 randomly selected tributary sample size were found to have the values, all of these values. To access the complete data set, click the link for your preferred software format. We have to download this from Minitab. Do the data give you reason to think that the springtime weather in the tributary water basin around Shavers Fork watershed is not neutral? Use the four-step process. State, is there evidence that the springtime water pH of the Shavers Fork watershed is not neutral? All right, so first we have to set up the hypothesis. Remember, when we perform an hypothesis test, first we have to set up the hypothesis. And we have to describe what the parameter is. In this case, the parameter is mu. Mu is what? Usually you will have to pay attention to the problem. Springtime water. Mean of springtime water. Just like that. If you want to write everything, you have to do this, right? So you identify what the parameter is. It says that neutral pH is the pH of pure water, that is pH equal to 7. So based on this sample, we want to test whether based on the sample, the mean from the sample is different from 7. So in this case, what are the hypotheses? Remember, always in the hypothesis, we have two hypotheses, H null and H alternative. Always in the H null, you need to have the parameter equal to something. So in this case, obviously it cannot be this option, right? Because it sets mu different. So it should be mu equal to something. In this case, it's going to be mu equal to 7 because the value, the neutral value is supposed to be 7. So here is going to be what? We don't have the the value from the sample by now to know how to uh, decide the alternative. So in this case, we're going to use only different. We're going to use this one. Mu equal to 7 versus the alternative mu different from 7. Find the value of the test statistic. This here, you have to find this by using the formula that I was computing before. Yeah, I'm sorry for that. But well, we don't have to do it by hand. All of this can be done by using Minitab. So again, you will have to download this in Minitab. You will have to download this to your computer and then upload this in Minitab. So I'm going to do it. Go to Minitab, File, Open, Worksheet, Local File. This is going to be Student Wildlife. And there you have. This is the data, right? You will have to download this to your computer and then upload it here into Minitab. Next, how to perform the hypothesis tests for the mean. You will have to go to Stat, Basic Statistics, One Sample T. Here, click the box Perform Hypothesis. Now the data is in C1. So C1 where the value for the pH are. The hypothetical value for the mean is the value in H0, right? The value in H0 or H0 is mu equal to 7. So that is the value you have to put here. Mu equal to 7. And then options. Here you will have to specify how the alternative is. We have three options, of course. Less, greater, in this case it's different, so you have to choose different. What about this confidence level? Ignore that. We don't need it by now. So okay, and then okay. There you have. What is the value of the test statistic? Is this one, p-value. And the p-value, what we need. So the t-value is negative 9.34. So the value for t is negative 9.34. What is the p-value? The p-value in this case is almost 0. So what is the option we have to choose here? I think the one is this one, p less than 0.001. And what is the rule? Remember, in all the hypothesis tests we're going to be seeing in this class, in this course again, is if if the p-value is less than alpha, reject H0. And what is the value of alpha, by the way? It doesn't say here. If it doesn't say in the problem, use alpha. The most common value is alpha equal to 0.05. So in this case, notice the p-value is almost 0 or it's less than 0.001. Obviously, it's less than 0.05, so we have to reject H0. 0.000 is less than 0.05. We reject H0. So what are we rejecting? We are rejecting that mu is equal to 7. The evidence goes in favor of what? That is different. So based on that, you will have to select the right conclusion. And in this case, it's going to be what? We have strong evidence that in this case, what they mean, by the way, because here it's a little confusing because it's using the mean was, notice here you have the mean for the values is 5.893, so it suggests that it's less. Yeah, I know. I don't know why this problem is mixing the alternative with different, and then here it says less. The options are only. I mean, less should say different. But well, I think this is something from Achieve. So we have external evidence to say that it's less than 7. So it's going to be this option, this one. Yeah, because the evidence, we reject H null. The evidence goes in favor of the alternative. Other example, counting steps. It says study examine the accuracy of consumer technology used for tracking physical activity. The report stated that when a random sample of 28 healthy adults each walked exactly 500 steps on a treadmill, the Fitbit Flex reported an average of 466 steps with a standard deviation of 93 steps. So note, this is the value for the mean and the standard deviation are given. The iPhone 5S Moves application by comparison reported an average of 531 with the standard deviation of 5 or 55. So here we have two values. I mean, we're going to be comparing, I think we're going to be doing here two hypotheses, right? Because we have one values for the Fitbit Flex and the other one for the iPhone 5S Moves application. Do these results provide significant evidence that this fitness tool report inaccurate numbers of steps on average? The figure gives the Minitab output for each technology. So this one is for the first Fitbit Flex. And this one is for the iPhone 5S. So this is like the information we got here in Minitab, right? But I mean, as we can put it in the previous example, but now we have it here. So we have to do only the analysis. So first, again, it doesn't say anything as to how to set up the alternative. We don't have the mean, the sample. We have the sample mean, right? So the hypothetical value should be for the Fitbit Flex application should be 531. So do these results provide significant evidence? All right, I'm sorry. First, for the Fitbit Flex, what is supposed to be 500? So do we have evidence to say, oh, the mean is 466, right? So it should be mu equal to 500 against the alternative less than 500, but we don't have less, right? So it should be mu equal, we are with the Fitbit Flex, so it should be 500 against the alternative less, but we don't have less than 500, so use different. So it's going to be this one. And for the iPhone, it's the same, 500, but the iPhone says it's greater, right? The iPhone says that the average is 500, but an average reported 531, so it should be greater. Should be this one. But I don't know why the right answer from achieve is different again. Well, I don't know why. I think it's this is a problem from achieve, right? Anyway, so I'm going to follow the right answer from achieve. Yeah, I mean the evidence says for the field reflex, it says that it's less than 500, and for the iPhone is greater than 500. So it should be this one, but no, the answer according to the right answer that I see on a chip for this one for both is actually mu equal to 500 versus different. Well, I don't know what. I mean, we can do this in this. We can do it different, right? But I think should be more correct if we do with greater. But well, anyway. Now, what is the value for the t in the what is the test statistic for Fitbit Flex? For Fitbit Flex, only check this one. The value for t is this one, negative 1.93. Negative 1.93. The p-value, this one, 0.064. So what do we do here? Use alpha. Again, it doesn't say, right, what is the value for alpha we have to use. So use alpha equal to 0.05. So if the p-value less than alpha, it is not, right? The p-value in this case is not less than alpha. So we don't have to we don't have to reject H null. So the answer will be there is not enough evidence to conclude that the Fitbit Flex reports an inaccurate number of steps. So we don't have enough evidence. We are not rejecting that mu is equal to 500. So maybe it is equal to 500. What happens with the iPhone? With the iPhone, the t is, again, go to this chart. The t now is 2.98 and the p-value 0.006. Very small the p-value. So 2.98 and the p-value 0.006. So in this case, notice the p-value is very small. It's less than alpha. So we have to reject the null hypothesis. So in this case, yes, there is enough evidence to conclude that the iPhone 5S moves application reports in an accurate number of steps. Yeah, in this case, for the iPhone, yes, we are rejecting this. We are rejecting that is equal to 500, so the evidence goes in favor of different from 500. Actually, it's greater, right? Because the sample for the iPhone was the mean from the sample was greater than 500. All right. All right, for this one, we have to use an applet that is given here. It says emissions of sulfur dioxide by industries set off chemical changes in the atmosphere that result in acid rain. The acidity of liquids is measured by pH on a scale of 0 to 14. Distilled water has pH 7. Lower pH values indicate acidity. Typical rain is somewhat acidic. So acid rain is defined as rainfall with a pH below 5. Suppose that pH measurements of rainfall on different days in a Canadian forest follow a normal distribution with a standard deviation of sigma equal to 0.5. A sample of n days find that the mean is from the sample is 4.8. Is this good evidence that the mean pH mu for all rainy days is less than 5? The answer depends on the size of the sample. Use the p-value of a test of significance applet for your computation. So you will have to click here, and a page is going to be open, and we will have to work this exercise by using this applet, this page. So, but notice the mean from the sample is 4.8, and the hypothetical value for the mean is 5. So notice they have correctly here the hypothesis mu equal to 5, alternative mu less than 5. Why less than 5? Because the evidence suggests it's less than 5. So here you will have to go to the web page, open it, and the web page is this one, you see? So you will have to type enter h null mu equal to 5, alternative less than 5, sigma is 0.5. All of this is given in the problem. That okay? All of these numbers are given here in the problem. 0.5, first n equal to 40. The observed x bar is 4.8. And there you have. The p-value is the first p-value. You have to pay attention to the first p-value. It's 0.00557. So for n equal to 40, this one, it is 0.0057. So what's going to happen to the p-value? We change the value for the sample size. Now it says then enter n equal to 5, 15, and 40. Oh, I'm sorry, I did it first for 40. Right now I'm going to do it for 15 and update every time. So here n is equal to 40. Now I'm going to change this to 15 and update. Notice it increased 0.0607. And finally for n equal to 5. N equal to 5, update 0.1855. So what happened to the what's happening to the p-value when we, well, I started with the 40, right? But that was my mistake. Anyway, no matter how we start this, I mean, what sample size? If we had started with n equal to 5, we will have 0.1855 at the p-value. Then for n equal to 15, the p-value is 0.0607, and the finally for n equal to 40, 0.0057. So what happened to the p-value as we are increasing the sample size? It is decreasing, right? Usually this makes sense because we have more evidence. Every time we have more bigger sample, we have more information from the population, so that is supposed to be better. That's why the p-value is increasing. All right. And then you will have to complete this. It says consider the three normal curves displayed by the applet with x equal to 4.8. Why are the p-values of the same results smaller for larger sample size? So the right answer here is at the sample size increasing, 4.8 gets closer to the of the sample distribution, which results in a small p-value. So this one. As the sample size increases, while everything else remains the same, x equal to 4.8 gets closer to the what? To the of the sample distribution, which results in a smaller p-value. Of course, it has to be one option where we have increasing, right? Because we are increasing the sample. So obviously it cannot be this one. So it has to be this, this, or this. But this one says 4.8 gets smaller. This value doesn't change. So it has to be this one or this one. But it says gets further on the tail of the sample distribution. No, if we have a more sample, then that means that this is supposed to be closer to the true value. Now, the corresponding 95% confidence interval for the mean would be, is given here, 4.36 to 5.24 for n equal to 5, and 15 and for 40. So we have three values for the confidence intervals for n equal to 5, 15, and 40. What information? Notice how the width for the confidence interval each time is smaller, 4.36 to 5.24, then 4.55 to 5.5, and finally 4.65 to 4.95. So the width for the interval, yeah, I mean the extremes, the endpoints for the interval are each time closer one to each other. So what information is conveyed by a confidence interval that we cannot learn from the p-values alone? The intervals, unlike the p-values, give a clear picture of what mean p is. The intervals, unlike the p-values, give a clear picture of what range of error is possible. For example, the p-values only give an estimate of the mean value, but they don't give an exact value. No, the intervals, like the p-values, give a clear picture of or what range of error is possible. I think it's the second one. The intervals, unlike the p-values, give a clear picture of what range of error is possible for each sample. All right. Now, identify type of error. All right, always when we are performing a hypothesis test, we can have two types of errors. So we can make two decisions: reject H null, do not reject. But H null, the hypothesis H null can be true or can be false. True or false. I'm sorry, let me put it here. True, false, reject, H null, do not reject. So we have, so whether we reject H null or we don't reject, always we are at risk of committing two possible errors. What happens if we reject H null, but it resolves to be true? In that case, we have a type 1 error. Type 1 error. And then what happens if we don't reject H null, but it's false? Again, other mistake. In that case, we have a type 2 error. So here it says, choose the correct description of a type 1 error and type 2 error in this context, right? Well, I will give you the answers because I don't want to make this video longer, but you will have to figure out why these answers are true, okay? In this one, it says, wait a minute. You know, I'm seeing here that the exercise is not the one that I have here. Oh, I'm sorry. Well, when I create the announcement of Blackboard to let you know about this, I will give you the answers for this exercise. Okay? Because I think they are different from the one that I have here. But yeah, I'm sorry. I need to investigate well what happened here. All right. Finally, compute the power. This is like in the lab. There is a lab for power in this module. So we have to do kind of the same here. It says, suppose that Forrester wants to see if the average height of lodgepole pines in Yellowstone is different from the national average of 70 feet. So this seems to be what? Like the hypothetical value, right? 70 feet. The standard deviation lodgepole pine height is known to be 8 feet. The forester decides to measure the height of 21 trees in Yellowstone and use a one sample t-test with a significant level of 0.01. She constructs the following null and alternative hypothesis, where mu the mean height of lodgepole pines in Yellowstone. And there you have these two hypotheses. And then it says, use software to determine the power of the hypothesis test if the true mean of height of lodgepole pines in Yellowstone is 64. You might find, so this is the value from the sample. This is X value. You may find one of these software might not useful. All right, this is if you check the video for the lab name power, you will know how to do this. But anyway, I'm going to do it here. First, you have to go to Minitab. You will have to go to Stat, Power, and Sample Size. In this case, you have to use one sample C. Sample sizes is 21. You see that? 21. 21 differences. How do we know what the difference is here? The difference is supposed to be the value, the hypothetical value minus x bar. In this case, x bar is supposed to be 64, and the hypothetical value is 70. So you will have to compute 70 minus 64, and the difference is 6. So you have to put here in differences 6. Power values, leave it in blank. We're trying to find that, and the standard deviation is 8.5 because it's given here, 8.5, and significance level is what is noticed is 0.01. So 0.01, and the alternative is what? Is different. So choose here not equal, then OK, and then OK. And the power is 0.7045. That's all what you have to do here. .7045. And there you have. All right, so the previous exercise, all right, is pending. I will let you know the answer because the constants. I don't know why, but I think the context of the problem it changed, right? But I need to verify that. All right, so the answers for this exercise, yeah, they're pending. I will let you know. See you in the next video.